Hello and welcome to today's PIR live event webinar brought to you by Partners in Research Canada. My name is Stacey Joyce and I will be your host. Please make sure that you ask questions anytime throughout the webinar if you're joining us live, clicking chat near the top left-hand corner of your screen, selecting in the to field, you want to select everyone rather than all panelists, and make sure you let us know with your question who's asking the question in your class, or perhaps your city or your school name, so we can give you a shout out when we ask your question. Today's guest is Dr. Daniel Alessi. He is the Assistant Professor and Ancana Chair in Water Resources in the Department of Earth and Atmospheric Sciences at the University of Alberta. Thank you so much for joining us today. I will let you take it away.
Great. Thank you, Stacey, and thanks to everybody out there for joining me this morning. So my group is essentially has expertise in looking at the environmental impacts of industrial processes. And most of my students now, my graduate students and researchers, focus on hydraulic fracturing. So the issues that might surround the development, the production of oil and gas from what's called hydraulic fracturing. So you can see in this cover slide here, that's an oil and gas rig there. So it's drilling a well down to great depths, probably a couple kilometers. And the point then is to get down into those rocks that have oil and gas, recover that oil and gas, and then process it for all the needs that we have, in our daily lives. Heating our houses, driving our cars, all those sorts of things. The process, you may have heard of the term hydraulic fracturing. So I just want to give you a real quick primer on what the process is so you understand it in case people ask you about it or you're just curious. The process is to first, you got to drill a well, right? So the first thing is we need to get a hole down into the formation where the oil and gas is. And for example, in Alberta or in British Columbia or even out east, those formations are usually down a couple kilometers. So it's quite deep, 2-3 kilometers. So what we do is first drill a hole. You can see I think this will work. There's a vertical part here. Hopefully you can see that. So we drill a vertical well, which is how a normal oil and gas well is drilled for many decades back into the 1800s. The newer technology is then to turn the well. So you can see this is called a target formation. What that means is it's the rock where the oil and gas is that we want to get. And so what we do is turn the well so that it goes horizontally into that formation. And that's a good thing, right? Because the more contact area, the longer this well goes into that rock, the more oil and gas we can get out of it. So that's the point. So we drill that well first. The rig that drills that well goes off site, and a new rig comes on, and what it does is do what's called the fracturing job. So they take a lot of water at the surface, so it's basically all water, mixed in with a little bit, some chemicals, and what those chemicals do is improve what's the performance of what's going to be the fracture. And we also mix sand into that. And what they do is put at the surface here a very high pressure pump. That pump then pushes this water, which is called fracturing fluid when you mix the chemicals in. So that fracturing fluid goes down the well into the target formation. And you can see here all these little fractures, right? So it's going to crack this rock. What that's going to do essentially is allow for that oil and gas that's in that formation to flow. So the fractures are down here, that oil and gas can then flow towards the wellbore. And the reason we do fracturing is because this rock is different than a normal oil and gas reservoir. So it's what we call a very tight formation. That is to say, unless we crack the rock, we couldn't get the oil and gas to flow towards the well. And that's the real new thing. That's what's been going on here the last decade, is this combination of these horizontal wells drilling horizontally plus the hydraulic fracturing. So you do the fracturing. When that's done, remember we have a lot of pressure on this well. So the fracture looks like this then, right? So this is kind of a zoom in of maybe down here. And that water goes in, fractures. Here's all the little pieces of sand. Remember we said we're putting sand down there. And those sands are going to hold open those fractures, especially the smaller ones further up. And then the natural gas or the oil will then flow towards the well. So what we do after we put all that pressure on is open up the well. And well, a lot of the water is going to come back first, right? So we put down a lot of water. Some of it's going to stay down there, but a lot of it's going to come back. And so the most important thing going forward, I think, is for you to understand the types of water. So if you remember anything, remember this. The two types of water are the fracturing fluid, and that again is mostly water. It's fresh water from usually streams or rivers or shallow aquifers, shallow groundwater. And that's what goes down the well. And once we do the fracture, the water that comes back up is called flowback and produced water. So that's the water that comes back up. And the reason we're all focused on water is, I just pointed out quickly, it's expensive. So for one well, it's about $2.5 million to do this process. And most of that money is in moving the water around in trucks and pipelines and all that sort of thing. the concerns, we'll just go through these kind of quickly here. But the first question is so here's that schematic again that you're familiar with now. The question is, let's say there's a bunch of gas down here. There's probably also some gas in some of these other formations. Can some of this gas, now that we've drilled a hole in it, get up to the surface and get into, see, this is called aquifer. So that's, say, the drinking water, the groundwater that we'd use at a farm or even in some houses, rural houses, for drinking water. The answer to that question is yes. And the reason that's been proven to happen, and the reason that it happens is, see this thin line here, this metal, that's a metal casing. And what they do between this metal casing and the formation is put cement. So in principle, that makes a seal so that nothing from down here can get up here. No gases from down here can get up here. But what happens in reality is if you go 10, 20, 30, 40, 50 years, those seals, that cement starts to fail. Just like on a building, right? If you look at a building that's 50 years old, the cement in that building is going to start to crumble and fail. Once that happens, there's cracks and there's pathways for gas to, say, go from, let's assume that there was gas in this formation, so a little bit of gas. Well, that gas can then migrate up the outside of the well bore, so using the cement as a pathway, and eventually get into this aquifer. Gas itself, natural gas itself, not that toxic. In terms of human consumption, I mean, you wouldn't want to have a lot of it. Everything's toxic, right? Toxic is a relative word. It means that depends on the dose, but gas in that, natural gas in that regard isn't a big concern. The big concern would be that it's natural gas, so it's explosive. And so if it's getting into concealed spaces like basements, for example, that's something we definitely want to start thinking about. Second is the land use. So you can see a bunch of hydraulic fracturing pads here, and this is an oil and gas field. And this landscape has been fragmented up, not just by the pads, but by the temporary roads that connect all the pads together. And even streams might get diverted in some cases. So if you're an animal living on land or a fish living in a stream, and suddenly you have to swim through a metal conduit, or you have to cross, as you're an animal that roams, you have to start crossing all these roads and dealing with the noise of the traffic, that may disturb your lifestyle, the ecosystem. And so that's a serious concern. There's air pollution. Remember, we just talked about the fact that many wells leak, and it's not just hydraulically fractured wells, it's all gas wells, essentially, even old ones that are conventional wells. They will leak, many of them will leak, not all of them, but many will, and that natural gas has a lot of methane in it, and methane is one of the biggest gases in climate change, so global warming. So, monitoring how much gas is coming out of these wells and going directly into the atmosphere is a concern. A lot of times the gas is flared at different steps in the process. So you can see that going on here. So instead of just venting it, we burn it. And of course, that's releasing CO2 into the environment, carbon dioxide. The reason we do flaring, for example, is during gas testing. So when they first put the well in production, they'll flare the gas. And what they do then is sample the gas as it's coming up. And that allows them to, once they get the chemistry of the gas, they can decide how to process it. That's probably one of the important steps. It's also flared for safety. So if there's extra pressure, you don't want that being released as a big methane plume, which is explosive. You instead want to have a process to burn it, and that's much safer, actually. It's much safer to have it burn there under a controlled environment than go across the landscape as a methane plume. And then there's all the engines, right? So there's generators on the site that are burning diesel and gasoline. There's trucks going in and out with a lot of water. We talked about all that water. It has to come from somewhere. So it might come in by trucks. The wastewater that comes out of the well, that's got to go somewhere. So it might go on trucks and go somewhere else. And that makes a lot of significant pollution as well. There's a lot of noise. I used to work on well pads in my younger years, and they're noisy. Now, if you go 300 meters away, you only hear faint well pad sounds. You can see a well pad here. This is a hydraulic fracturing well pad that maybe isn't particularly well designed. It's close to a building here, a school, I believe, and then a bunch of houses. Now that's pretty far away maybe, but it's still, you can hear the faint noises, and it's been shown clearly that even these low-level noises can reduce people's quality of life. They don't sleep well, they get stressed out, they get headaches, they don't do as well at school. That's shown. Some positive things that have happened is different jurisdictions, so different government authorities have increased the setback, so that's the distance between the well and the building, say. And also there's been a sort of a growth in noise monitoring and also noise scientific studies. So those are good things. And you may have heard of earthquakes. So does hydraulic fracturing cause earthquakes? Well, every time you fracture rock, so keep in mind, first off, again, this is happening down several kilometers at least, so way in the subsurface. When you crack the rocks, there is some shaking involved with that, but it's very low level shaking. So we wouldn't call it an earthquake, we would call it a seismic event. And we can measure it. We have instruments that are very sensitive to measure it. But the point is, almost every single well that you hydraulically fracture at 2, 3, 4, 5 kilometers, you will never, ever in a million years feel that at the surface because they're such small shakes that you can't feel them. But once in a while, and this has happened in Alberta, it's happened in British Columbia, and Oklahoma, and Pennsylvania, once in a while when you pump that water down there, you lubricate or you activate existing cracks in the rock or existing faults in the rock, and then you can have a significant slip, right? And those slips are the ones that are thought to cause the earthquakes that we can feel at the surface. So the ones that have happened in northern Alberta, in western BC, British Columbia, and I would say those earthquakes, they should be called earthquakes. Those earthquakes are not big ones so far. So if you were standing in a building and in your kitchen, could you feel it? Absolutely. You would shake and you'd definitely be startled and say, what's going on? But they're the types that are going to shake plates and that sort of thing. It's not the type that's going to ruin structures. But there's a concern around that. You know, the question is, could there be bigger ones? Very good question. So people are studying that. I also said that there's a lot of wastewater produced, right? So remember the water that we put the water down and flow back and produce water comes back up. Well, that water is put on trucks that leave the well pad and they go somewhere else. So they go into a wastewater injection site. So they drive the trucks maybe 10, 20, 100 kilometers away, and they inject that water into a different, deeper formation. Now, this also can cause earthquakes for exactly the same reasons I was talking about before. Has nothing to do with the fracturing itself, but that wastewater is going into a disposal well. And, well, it's the fracturing, any water can cause that, but it's the fact that there's a lot of water being generated from hydraulic fracturing that has caused an increase in these these wastewater injection well events. Okay. And to close up here in a few minutes, hydraulic fracturing also uses fresh water, so we talked about that. And I just want to point out from a study that I did this year, these are all the wells that were drilled in this 2.5 year period between 2011 and 2014. Each one of those is a separate well, and so you're talking about almost 4,000 wells over 2.5 years. So this is not a process that's rare. I mean, there's thousands of wells and there's tens of thousands of wells in the United States. And some of them, the big ones, you can see the blue ones up here in British Columbia, well, those use sometimes more than 20 Olympic swimming pools of water, just to give you something that maybe you can wrap your head around. So if you've seen a big swimming pool, imagine 20 of those pools. It's a significant amount of water. And the bigger concern is a lot of that water is going to come back up. And so the question is how to deal with that water. What I didn't tell you, and I'm telling you now, is the water that comes up is not like the water that goes down. So the water that went down was like fresh water. It was essentially drinking water with some chemicals added to it and some sand. When it comes back up, you can see it's quite a bit different. So its chemistry is very complicated. It even has microorganisms, so bacteria that grow in it. And it's also potential, so it's very, the fact that it's very complicated makes us wonder, I wonder what it does if it gets in contact with organisms, you know, things in rivers, for example. And so the point of our research program here at the University of Alberta has been to understand the composition of that water better. We work with Encana, who's based in Calgary. So they're a big oil and gas, mostly gas company. And they share with us the fluids from these sites because they're interested in improving their process. So that's recently a lot of the companies have been interested in improving their environmental performance of their operations. So here I am with, this is John Martin, one of the professors I work with, and some of the other students. And this is the guy who works in this is a building on the oil pad site. And he's giving me, the flowback water is coming right into this tank behind John's head here. He's giving me a sample of that water. And so here's a picture of what it looks like, right, when it comes back up. It's really salty is the first thing to say. So it's maybe 6 or 7 times saltier than seawater, and seawater is pretty salty. So that's one concern. It also has a lot of chemicals in it. So here's an example of an analysis that Professor Martin does in his lab. But the main thing to understand here is that each one of these little peaks here, they're all different sizes, but every single peak you see is a separate chemical compound that wasn't present necessarily in the water when it went down. Some of them were, but there's a lot of new ones as well. And so our question of a research program is, you know, each one of these things, some of them might be completely harmless, some of them might be quite harmful. And the question is, which of these things here are causing harm to organisms or might cause harm to organisms? So it's a complicated project it's a 5-year project. So the other collaborator is Greg Goss. He's this guy here. He's a professor on biology. And what we do in Greg's lab here is we grow different organisms. So in this case, there's fish being grown here. And what we do is expose those organisms to the fracturing fluid or dilutions of the fracturing fluid. Now that we need to do that, and that's because it's the only way we know to assess the impact of fluids like this on aquatic ecosystems. And the government, the provincial and the federal governments, really need these data in order to be able to set regulations and safe guidelines, right? So these studies are quite important that we carry them out. Here's an example of, this is a zebrafish embryo, so it's a very small fish, a juvenile fish, and just some of the impacts we've been seeing. So this one you can see has a little bit of a bent spine. For the medical, for those aspire to be doctors, this thing here is what's called, this little bubble here is called a pericardial edema, so it's just water on the heart, and that's not good. And this one's hard to see, but there's actually, if you look closely, there's a lot of sediment, so that's stuck to it. So little particles in the water. Remember, we looked at the water, it was kind of this cloudy orange color. Well, a lot of those particles actually stick on the side of the organism. So here it is again, looks rusty color, it's got this orangish yellowish color. In my lab, what we do is we take that sediment, you can't see it with your eye, but we use what's called an electron microscope. And so we're looking at 20,000 times your eye vision, essentially. So it's very, very, very magnified. This is 1/1,000,000th of a meter, micron it's called. And you can see the little rust particles. They're very tiny little rust particles. So we verify that. And what's going on, definitely don't have time here to show all the data, but these rust particles form in the flowback. So it comes to the surface clear, and the solution essentially rusts, just like your car would rust, but it goes much quicker. Those little particles form that we can't see. Compounds, remember we showed that picture of all the little peaks, well, some of those compounds stick to the side of this rust particles. And then what we found is, I showed you the picture of the fish, but those little particles and those little pieces of rust have potentially toxic or hazardous compounds stuck to them. And it ends up that we found out that these little pieces of rust will stick themselves to the side of like fish, for example. So what these things are doing, then, to be very clear, these are acting as a delivery mechanism, right? They're a pathway of delivery for these toxins right to the side of the organism, right to the side of a fish, for example. And so we're concerned about that, of course. And we're also thinking, on the positive side, what we might be able to do is remove these particles at the well pad and make the waters a lot safer as they're being trucked to be disposed. Yeah, I'll just close with the general statement. So I've given, I guess, a lot of positives and negatives of the process. The one thing to remember is that, our entire society is run on having minerals and oil and gas that are mined from different locations, right? So your iPhone has metals mined from open pit mines. The buildings that we sit in right now are being warmed by natural gas or some other fuel, perhaps coal. If you took a bus into school or your parents dropped you off, that fuel had to come from somewhere. It's very important to understand that every single thing we want in society, any processed item that we want, has an environmental impact behind it, a cost to water, a cost to the carbon footprint. I think the point of our research here has been to say, hydraulic fracturing is one of these of a million processes that are going on, in this case to get natural gas. We're looking at this process, and the point of our research is to try to make that process more friendly. So I'll close with that and pass it back to Stacy.
Well, thank you so much. If you want to click on stop share there, we'll see your video a little larger.
Great, thanks.
Excellent. So our first question comes from the grade 5s at Fossil Hill Public School. They are in Woodbridge, Ontario, and they would like to know how fast the flowback comes out.
Oh, that's a very good question. So when the well is first fractured, right? So when you put the water down there, it's at very great pressure. So it might be hundreds of times the atmospheric pressure, for example. And so initially, when you open the well, you get a lot of water in a very short period of time. As you go on, then what happens is, so in the first few hours, you're getting quite a bit of water. As you go on in that process, you're getting less and less water, but the water is also getting more and more salty as you go on. So you're getting water that's, in the beginning, you put down a lot of fresh water and you're getting a lot of that back. And as you go further in time, so day 2, day 3, day 4, day 10, you're getting water that's more like the formation itself. And the formation itself, at least in Alberta and British Columbia and a lot of places in the US, is quite salty. So you've got this kind of interesting thing where the first water is quite fresh, and actually a lot of that is reused. And as you go on in time, you're getting less water, but it actually has more environmental concerns attached with it. So there's a little dynamic going on there, I guess.
And when you say it's reused, is it reused at another well or the same well? How does that work?
Definitely, normally not the same well. I mean, there's a lot of options, right? So it can either be treated and reused. A lot of times what happens is, if it's salty enough, it's mixed back into fresh water. So they might mix, 15% of the water that comes back, with 85% new fresh water. And what that allows, it saves money, of course, because, you know, instead of trucking that water off and paying the cost to have it disposed, it's being reused in the process. That being said, the vast majority of water, even to this date in Western Canada, is deep well injected. So it's taken off-site and deep well injected.
Excellent. We have another question here, this time coming from Edgemont School in Calgary. Olivia would like to know, have you tested the effects of flowback water on other organisms than fish?
Yeah, so the organisms so far, I believe there's 3, because it's in Professor Goss's lab. So we've done, the one that was publicized really well was trout. So there's quite a few articles on the exposure to trout. We've done the zebrafish, and the other one we've done is what are called daphnids. So these are water fleas, essentially. Very tiny little water fleas that are easier to grow. The important thing to understand about why we would select it, so you might say, well, why are you working on these organisms? It's a great question. The reason is that basically everybody uses them. So they're what's called model organisms. So it might be that if somebody else conducts a study and they do it also on Daphnia, which is this water flea, well, then we can compare those 2 studies directly. So we always start with model organisms, and then, you know, that allows us to set sort of regulation based on a standardized set of organisms.
Okay, and next we have a question from Ms. Pramack's class in Ontario. Why, as 10 to 12-year-olds living in Ontario, should we be concerned with the impact on organisms? What does this mean for us? Well,
this is the broad, I guess, question that you are in Ontario, that's fair, but Canada is your country, so you know what's happening in Western Canada now is, I would say, should be of concern to everybody. I mean, this is happening, and you know the process is going on widespread in 2 provinces. And the other thing to say to that question is, it's very likely that hydraulic fracturing is going to start out in the east. So there are oil and gas deposits in, say, Quebec and out in the Maritimes that are being prospected, and there's interest in the governments to start pursuing those resources. So if that happens, that process is going to be closer to home, right?
Mm-hmm. And that brings us right to the next question. You're creating this flow for me here. Ms. Kay's class at the Edgemont School in Calgary asks, how do you choose the land in which fracturing occurs?
So, well, it depends on where the resource is, right? So I guess I'll venture to describe it briefly, but if you go out to Fort McMurray, so Fort McMurray is up kind of by the Saskatchewan border, that's way out west, right? Way out east, right? And that has very thick tar sands, so very thick oil. And it's called bitumen, in fact. And as you get closer to the mountains, so closer towards, say, Calgary or Edmonton or Grand Prairie, the formations get what are called more and more mature. So we start transitioning from a very thick oil to a regular oil to a really thin oil, and then we start transitioning into gas. And so what these companies do is they look at what kind of product they want to get. So it's sort of like a buffet of products from the mountains, which is almost pure gas, well, before the mountains, but up against the mountains, going to really thick tar sands. And so you would target your wells depending on what kind of product you want to get out. And of course, also what the geology looks like under the ground, right? So oil and gas isn't everywhere. So you have to do some prospecting and some analysis of the reservoirs that are called oil and gas reservoirs and decide where to put your wells.
Okay, and Jack and Noah would like to know, why does it have to be fresh water? Can't we use seawater for hydraulic fracturing?
It depends. That's a very good question. It depends on the formation. So it ends up that salty water doesn't work well for fracturing some formations. And the reason that is well, one of the reasons is when there's clay in the formation, for example. So this is something for more of a geochemistry class, but when you put a clay in salty water, or many clays in salty water, they expand a lot. And so if you have clays in the formation you're targeting and then they start to expand, remember that we were trying to make fractures, well, those clays can fill the fractures and make the project less successful. Some formations, actually, seawater would work. And there's a lot of work going on in the companies that make these chemicals to make chemicals that will work in saltier waters. So that's a progress. There are cases where have been fractures done with water that's more salty than the ocean. It's possible, but it's not the common thing. Typically, fresh water works the best.
Okay. And a few more questions coming in here from Mr. Thomas's class at Edgemont School in Calgary. Jode would like to know, how is the flowback water treated, and can it be made potable again?
Well, the first thing I'll remind, I guess I remind that most of it is not treated. So unfortunately, it's deep well injected. And the reason for that is there's really no incentive to treat it. It's much less expensive to deep well inject it and take new water than it is to treat it. The treatment that goes on, well, there's a lot of different ways it's treated. The first one is just straight recycling. So we do essentially no treatment to it or minimal treatment, and we take some of that water and dilute it back. I think I mentioned this before. We dilute it into fresh water. So maybe 1/7 flowback water and 6/7 fresh water, and that way you can reuse some of it. There's membrane technologies being tested out. So can we do filtration, for example? All of those things are expensive, especially with the volumes of water that we're dealing with. To answer the question directly, could it be treated back to fresh water? Absolutely. Any water in the world could be treated back to fresh water. But the question here is not whether we can do it, it's the expense. And so let's say you have, I didn't give numbers before, but let's say we were talking about 10 or 20 Olympic swimming pools of that water coming back up that need to be treated. The cost of treating that water back to drinking water would be immense. I mean, millions and millions and millions of dollars. And so it's just sort of economically not feasible to do it, unfortunately. That's why it's not done.
I see. And now we have a question from Hay Lake School in Alberta. The grade 8s there would like to know how much oil is pumped up per day, and therefore how much fresh water needed. So I'm not sure if you have the answer for oil, but if not, perhaps we could talk about natural gas.
Okay, so the amount of gas that you get out of a well completely the answer is it varies widely. So it depends on where the gas well was. And the other thing is, even when they drill the wells, they have reasonable estimates of what the gas production might be, but you never really know until you put the well on production. And so they're constantly making decisions about, is the well meeting a performance? If they're not, sometimes even go back and they'll refracture it again, so they'll fracture it a second time. And yeah, I guess that's about it. I can't give you a fixed number on that. I don't know what the actual volumes are, but it does vary widely by well and by formation, essentially.
I suppose that makes sense. They're not exactly regulated pockets under the ground of natural gas. We're extracting whatever we can, and they must vary in size, I assume.
That's right. Yeah, and where you are in the formation exactly. I mean, they do of course, the geologists that work and the engineers that work for the oil and gas companies really know what they're doing. But even that being said, sort of they're trying to assess the reservoir, right? They're using a bunch of scientific techniques to say, what does the oil and gas reservoir look like? Where should we put our oil and gas wells? What's the best spot? All that said, I guarantee, a lot of them, they still hold their breath for when they open the spigot and see how much oil and gas comes out. They're saying, okay, were we right? Weren't we right? There's some variability in that still. So it's still prospecting. It's still a little bit of fun left in that, I think, in terms of.
I don't know how many of them would think it was very fun as they're waiting to see whether they were correct or not. But Ms. Kay's class in Calgary wanted to ask if so you mentioned deep well injection of the flowback. So does the flowback water just sit there underground? Where would it go? And besides earthquakes, are there any other implications for hydraulic fracturing?
So it's deep well injected in formations that are often, almost always, deeper than the formations that are being fractured. Does it move? There's deep groundwater systems. So yes, it's very, very slowly. That fluid wouldn't, the rocks formations into which you're doing that deep well injection are, you'd have to know the geology of Canada, but they don't reach the surface for thousands of kilometers. And so essentially that fluid is, while it may have some toxicity, it's essentially lost into that formation for, hundreds of millions of years at least. And I would also say that the water that's in that formation already, so you say, okay, well, you're taking that water and putting it into a formation. The water that's in those deep formations is already quite salty, so it's not really contaminating an aquifer that, it definitely doesn't have drinkable water down that deep, so it's not contaminating a freshwater resource or anything. And sorry, there was a second part of the...
Oh, are there any other implications that we haven't discussed yet besides earthquakes for hydraulic fracturing?
We did land use, noise, methane migration. And I guess I would just re-emphasize, I don't know if I did a good job of this, but the fluid, right? So the flowback fluid that comes to the surface, the major concern around, just briefly, the major concern around that is, I said it comes back up, we have to put it on a truck. Normally, some of it's recycled, so we had some other good questions about that, but mostly it's put on trucks and it's driven to one of these injection sites. So once in a while, a pipe will break or a truck will have an accident or something like that, and that's how we get surface spills. So I'd just like to emphasize that the main concern around the flowback is that it sometimes gets spilled at the surface. And so if we get these spills, what happens? The final quick comment is those are really rare. So the oil and gas companies in Calgary and Edmonton, mostly in BC, I guess, they have pretty good environmental practices, I would say now. I mean, certainly these days it's well regulated. So if you look at the volumes of water that they're dealing with versus the volume of spills, it's very, very little bit of the stuff that's actually spilled. That being said, it's still worth studying, right? I mean, we still want to know when this happens, what's going to happen to the ecosystem. So that's what the point of our research is.
Well, thank you so much for all the wonderful information that you've given us today. Before we wrap up, is there anything else that you would like our audience to know about hydraulic fracturing, about what it's like to be a researcher and collaborating, or any advice if they're interested in pursuing studies in this area?
Yeah, I mean, I guess I would say, well, I guess I'll focus on the being a researcher in this area. I mean, if you're interested in solving problems for a living, I think being a scientist or an engineer is very fun. So I enjoy, definitely talk to your science teachers. You know, they obviously are teaching you the basics of science. Here we have a research lab. So one of the joys, and believe it or not, as a university professor at a place like University of Alberta, I don't do that much teaching in the classroom. So I may teach 1 or 2 classes a semester. But I spend a lot of time with my students in the laboratory. So my undergraduate students, a lot of you are going to be going off to university, undergraduate students and my graduate students and my researchers, solving problems every day. And I think that's really satisfying, right? Especially on these applied problems like hydraulic fracturing, where you can see, you do some research and you can see an impact on the environmental performance of, you know, these operations in this case. So.
Well, thank you so much for joining us today and making us all a little bit more knowledgeable about hydraulic fracturing in Canada.
Great, thanks, Stacey, appreciate it.
Next up on PIR Live Event, we are continuing our water-based theme as we learn about invasive species and other threats to Canadian waterways. More information on this and other PIR Live Event webinars is available at pirweb.org. Thanks so much for joining us and have a great day, everyone.